Hi, this is Javier Encinas, and today we're going to design completely from scratch a beam to girder shear connection in a real-life example using our software ASDIP STEEL. This is a multi-story storage building. This is the partial framing plan of the second floor. The first level will be dedicated to retail spaces with a wider column layout. The second level and up will be dedicated to storage with the columns are more closely spaced. So this type of transfer beams and girders will be used to support the columns at the upper levels and allow for open spaces at the retail. The member sizes have been already specified as part of the design of the building. The beams are W24 by 62 and the transfer girder is W30 by 99. Also, as part of the analysis of the building, we have found the beam reactions at this particular location as 18 kips for dead and 24 kips of life. Note that the beams are connected at each side of the girder. So let's get started. When you open ASDIP STEEL, this is the project manager where you can see all the modules included in the package. In this case, we're going to use the shear connection module. Let's create a calculation for this. Let's call it beam to girder connection. So we are creating a calculation already. It's added to the tree. Double click on the calculation that you just created, and this is the typical calculations for a shear connection. All these values are default. They don't mean anything to this particular example, so we can change whatever we want to change. The first thing that we need to decide is what kind of connection we're going to use. We have four options: single angle, double angle, single plate, or T connections. Let's analyze what would be the best. First of all, we need to note that the beams are connected at each side of the girder. So if we use a bolted connection to the support, the bolts will be common to both sides. In other words, if I put a bolt through the web of the girder, the same bolt will be used for this connection and for that connection. That means that this beam and that beam would need to be erected simultaneously, which is not a very desirable condition. It's difficult to do at the field, so we could try to avoid that. So the first decision we need to make is that in this case we don't want to use bolted connections to the support. We would prefer welded connection to the support. Okay, if we use a welded connection to the support, then the double angle connection probably is not the best option, because this type of connection by default will be welded to the beam and bolted to the support. Another option is to use a single angle connection. This type of connection could be welded to the support and bolted to the beam, just avoiding the bolts through the support web. Another option would be, for example, single plate. That would be easy to implement at the field. Basically, would look like this. So one plate on one side, another plate on the other side. Both are welded to the web. And finally, T connection is also possible, but needs to be again welded to the support, not bolted. For this example, we'll use a single angle connection. Let's get started. We know from the statement, we know the size of the members, so let's input that. The girder is W30 by 99. Here, the support, the member. Let's input the member size from the AISC database. is 30 by 99. So select that. It's already input there. Then we go to the beam. We know from the example statement that the beam is 24 by 62. Let's input that. (24 by 62). Select that size. So we have already defined the sizes of the girder and the beam. We know here that we have a problem because we need to cope the top flange of the beam. Otherwise, there will be a conflict here. So we need to cope it. Top flange is coped. Click on that, and then the flange is coped. We can select the dimensions here as necessary. We can change the width and the height of the cope. With this 6 and 2 is good enough. So we are okay with this coping. We are connecting to a beam web. It's also possible to connect to a column flange like this, or a column web, or to a beam web, which is our case. We are connecting a beam to a girder. So this is beam web connection. So we have already selected the beams and the girders. In this case, we are telling the program that another beam is in the other side of the girder. So we are clicking here a similar connection on the other side of the support, meaning that the support will be, we have twice the load. Yeah, we have that. We have already specified the beam size, and now the gap is 3/4 of an inch. This is the distance between the space between the web and the beam. So we are leaving, 3/4 of an inch space gap in between them. So it's okay. We already coped the top flange, so we are done with that. The angle. Okay, we need to specify the connector, the angle. We need to input the loads that are known, 18 dead and 24 live. So we're using a nominal set of load cases. We said 18 dead and 24 live. So we have already input the loads. We have already input the member sizes. So let's proceed with the design. Let's go back to the angle sizes. We said originally that the member needs to be welded to the support. Angle at the support needs to be welded. So now it's welded versus bolted. Now it's welded. And we're gonna continue with bolted to the beam. Could be welded as well, like that, welded, but probably it's easier shop weld to the support and field bolted to the beam. We need to specify the number of bolts. Let's go to the tab bolts. We have 3 bolts now, 3 bolts. Obviously, a lot of failures here. Let's increase 1 more bolt, 4, 1 more bolt, 5. With 5 bolts, we have everything passing. Graphically looks like that. 5 bolts every 3 inches. Let's go back to the angle. Here, we have an eccentricity of 1 inch that we actually don't need. We probably specify 0 eccentricity so that the angle is completely centered with the beam, just like that. Okay, here probably we should specify an angle 4x4 just to have more room for the bolts at the field. Okay, we have this condition 4x4 by 3/8 is the angle, 0 eccentricity, and edge distance. So we have specified 1 1/4 and 1 1/4, which is okay. So basically we have this condition in front view. We can see the angle welded to the web of the girder and bolted to the web of the beam. The beam is coved, and we are using a single angle connection. Regarding the materials, well, the beams are 50 KSI and the tensile strength 65. Same thing for the beam. The angle and the bolts, we are using 3/4 diameter or 325 high strength bolts, and the weld we are specifying 1/4 inch fillet weld with electrode 70. We entered the loads already. So let's focus on the results. We can see in this scenario that we are everything passing. The maximum load combination, these numbers, is 42. Actually, we can see it better in this view in condensed. We can see that the controlling combination is the first one, which is 42 kips, and the controlling, so the minimum capacity of the limit states is controlled by the bolt shear rupture, which is the bolt itself in shear, which is 47.8 versus 42. So we are okay. The ratio is 88% of the designs, which is very well optimized. The design checks, which checks the minimum angle thickness and the minimum weld, is passing also. So this design is very acceptable, is okay, it's optimum as well. In the condensed report, you can see more information with all the geometry and the materials, loads. We can see here the different limit states of the connection strength with omega, and the nominal reaction for nominal capacity for every single limit state, and the design capacity. The design checks, you can see here what is applicable to this type of connection. The others are just ignored, don't apply. This is a check of the geometric constraints of the connection, particularly the connector width, the support or at the beam, the connector length, and so on. The detail tab shows more step-by-step detailed type of connection report with exposed formulas and a reference to the code. It's also organized by topic and by limit state. So the capacity is developed here step by step for a granular checking. Finally, graphically, you can see the three views: front view, looking at the girder web; side view, looking at the beam connecting to the girder; and top view, where you can see the connector. The design summary: we are 88% of the capacity in strength. The design check is 83%, and the geometric constraints are okay. You can create a report of the condensed tab or a report of the detail tab. Go to this icon. This is the print preview of the report, the condensed report. Let's create that. Looks like that in 2 pages. It's a pre-formatted report where you can see all the most important information and also the images. Same way you can create a detailed report. You can see all the pages. Five pages. It's also pre-formatted with all the information, the calculations, reference to the code, and the images as well. So you can print out this and pass it to your coworkers, to your checker, or to your client. Many limit states account for the eccentricity of the connection, and that's accounted for in the program based on the instantaneous center of rotation theory in the AISC. So internally, the program calculates the capacity according to that theory, and that's reflected on all these numbers in the connection strength. The design criteria, you can specify if the eccentricity is neglected or considered for the single angle, double angle, single plate, or the T-connection for bolted connections or for welded connection. Okay, this is the design of a single angle connection of a beam to girder in a real life building. So thank you for your attention. We'll see you in the next video. Thank you.